From arid volcanic landscapes close to Teide volcano to vertical rocky cliffs by the northern coastline, Tenerife landscapes are breathtaking. But to the eye of geologists, the layers of rocks are not just landscapes. Each of them is a book which can be read to tell the history of Earth through geologic time. It is in southern Tenerife where an international group of students and professors from GeoTenerife are spending hours under the sun describing in detail amazing exposures of pumice layers, volcanic deposits from an explosive volcano which in the last 2 million years accumulated in layers forming the south of the island. This will help them to understand how often these eruptions took place in the past, which will help them to get to know better the present and future behavior of the volcano and the risks associated to this volcanic complex, which nowadays is controlled by Teide volcano. West of the African continent, Tenerife is the biggest of the islands of the Canarian archipelago, formed by rocks coming out of oceanic volcanoes. Its landscape has changed across time. 3 million years ago, there used to be a shield volcano called Las Cañadas at the same volcanic complex where Teide volcano is right now. Las Cañadas used to generate Plinian eruptions, explosive and devastating eruptions which can produce ash columns reaching up to 50 kilometers height and can travel around the world and even affect the global climate.
Plinian eruptions start when magma fragments and exits the volcanic vent at very high velocities, several hundred meters a second. That material is ejected into the air and it mixes with the surrounding atmosphere and it heats up the air, and the whole mixture becomes buoyant, becomes less dense than the surrounding atmosphere. That material, which is composed of ash and pumice, then rises convectively through the atmosphere to form an eruption column, and when it reaches a level of neutral buoyancy, so essentially the density is the same as the surrounding atmosphere, and this could be anywhere from 5 kilometers above sea level to 40 kilometers above sea level, that material then becomes advected by the wind. So the wind field at that height then blows that material downwind, and so it spreads out across, in this case, across the south of the island, and progressively as it spreads out, the pumice falls out of that eruption cloud and settles on the ground, much like a layer of snow.
Bandas del Sur, in the arid south of Tenerife, is a site of interest for geologists, as it has the record of deposits from the Plinian eruptions of Las Cañadas. Up till now, scientists believe that these layers are the record of at least 40 Plinian eruptions in the last 2 million years, with an average concurrence of 40,000 years between each. These eruptions happen in at least 3 eruptive cycles, forming 3 calderas still visible nowadays. But how accurate is this information? Volcanologists believe there are still undescribed explosive and caldera-forming eruptions hidden in the rocky layers of Bandas del Sur. Interested in studying the past to understand the present and future risks related to this volcanic complex, professors and students in GeoTenerife have taken the task to find them, under the guidance of expert volcanologists in Tenerife, Dr. Richard Brown and Dr. Alexis Schwartz.
So, what are we looking at here?
So in this quarry we see a number of pumice fall deposits exposed in the surfaces of the quarry, and these are the products of explosive volcanic eruptions from Las Cañadas caldera, which is 20 kilometers to our northwest. They're made of pumice, and pumice is a very light, frothy material. It's basically bubbly magma, frozen bubbly magma, and the pumice got here via travelling 30 kilometers up into the atmosphere during an explosive volcanic eruption, and then being blown by the wind over the south and the east of the volcano.
Bandas del Sur has multiple undescribed pumice fall deposits. Some of these could relate to unknown volcanic eruptions from Las Cañadas volcano, and by studying them, we can get closer to the biggest scientific question. How many Plinian eruptions have occurred at Las Cañadas in the last 2 million years?
Okay, so this exact unit, do we know how old it is?
Well, that's part of our job, and so some of the units here have been dated. So we have methods whereby we can ascribe an absolute age to when the eruption happened. A lot of these deposits haven't been dated, so we have an understanding in a relative sense of how old they are, because some units higher up or some units lower down have been dated. So these are all of the order of a few 100,000 years old, and we don't know exactly how old they are. And that might be something we'll address in the future once we've understood these deposits a little bit better.
Amazing.
Our work now is to try to identify fault deposits between these known ignites. So in order to complete the record of eruptions in Tenerife.
The method to describe these pumice layers is called stratigraphy, which is commonly used in geology for ordering the relative positions of strata or layers.
You want to describe in detail how the deposit changes with height, and we record that in a stratigraphic log.
By making stratigraphic logs and describing the thickness, shape, size, and composition of the pumice, students are learning to recognize the physical characteristics of each of the layers and to correlate this with other layers they see in different localities and with previously peer-reviewed studies.
We need to describe this layer here and then another layer there, and then compare it with the other guys there, which are looking at something similar. So
the reason why this group is spending hours digging and scratching in between the pumice layers, it's because the accurate description of this will allow them to understand the characteristic of past volcanic eruptions, which can relate to future potential ones.
Using these deposits to work out where on the island they were deposited, so when there was an eruption, which direction was the wind blowing. For a lot of these deposits they were dispersed over the south of the island, but some of them went over the north.
Okay.
In other places some have gone over to the west. Measuring the size of the particles in these pumice fall deposits, and by applying simple mathematical models we can use the rate at which those particles decrease in size in the fall deposit to tell us how high the column was. There's an empirical relationship between the distribution of clasts of a certain size and the height of an eruption column.
Large-scale explosive eruptions are one of the most serious natural disasters on Earth, as they often result in a large area of devastation, especially in areas where population is concentrated close to explosive volcanoes.
Why is it important to study these deposits in Tenerife?
So that's a really good question. So Tenerife in the past has experienced some really big volcanic eruptions, and should one of those eruptions happen in the future, these explosive Plinian style eruptions, it would pose a great threat to people on the island. So in the past these eruptions have covered large parts of the island with thick layers of volcanic ash and pumice, and also generated pyroclastic flows, these hazardous clouds of ash and pumice that travelled down the flanks of the volcano many tens of meters a second, very destructive. And so by digging into the geological past, by looking at these layers and working on them, researching them, understanding something about them, we have a better idea of what might happen in the future and how we might mitigate against the hazards that they pose. So mapping out these pumice fall deposits is really important for understanding the spatial distribution of risk from future eruptions. And in terms of predicting what would happen during a future eruption, we would want to look at that statistically. So we'd want to know, how many pumice fall deposits have been dispersed over the south of the island. Which directions have they gone in general? And then, because you can use that information to build hazard maps for the future, which will give you an idea of a probability. So if there's a future explosive eruption on Tenerife.
Like in every other science, geologists take a long time collecting their data. For the GeoTenerife students, this is a test for their future professional careers.
It's a test to come here and do this tedious job for a week, because in reality, you do this for months, honestly. To be able to decipher the whole stratigraphy, people have spent months and months and still they got it not very right, and then later on people came and corrected a few things. It's a question of a lot of time and a lot of work. Got strength physically because you need to be strong to be walking all day, but then you have to have a very strong mind to be able to do all this very repetitive and tedious work day after day without losing heart.
Right. And doing it well, passionate.
Yeah.
That's correct.
And the excitement of being involved in new research is shaping them as future scientists.
So we describe the stratigraphy that wasn't described in the books, in the literature. And personally, I already have done that, but I've never done it when it wasn't in the literature. So I find it quite like rewarding because it's gonna study it afterwards, and we're doing like new thing that it's like new research.
But this is the first time that I'm really, I think, more actively contributing to research with studying hazards and understanding risk, and that's kind of what I want to do with my life. So it's good that I'm doing it now.